Okay, in this video we're going to be reviewing for the Performance Task 6 test. So we're going to start by looking at the relationship between wavelengths and energy. This first picture is showing a long wavelength that has low energy and low frequency. And the second picture is showing a short wavelength that has high energy and high frequency. And how we can tell it's a long or short wavelength is because of the distance between these peaks. So that's a pretty long distance versus this one is a pretty short distance. So that's a short wavelength and the one on top is a long wavelength. And the relationship between these two is an inverse relationship, which means as one goes up, the other one goes down. So as the wavelength gets longer, the energy gets lower. And as the wavelength for the second one gets shorter, the energy gets higher. So that's an inverse relationship. In the next example, we're going to draw some models. So if atom number 1's electron drops 3 energy levels, okay, and atom number 2's electron drops 1 energy level, what light will be given off by each? Label both atoms on the wave below and draw a model showing shells and electrons for each. So we're going to draw a very general model, not like the Bohr models that are specific, like these ones that you see here, that, you know, you're drawing one for sodium or oxygen or neon. They're going to look similar, but it's not a specific atom. It's a very general model. We just have to show the change in energy for these models. So let me start by drawing the shells. Okay. Let's copy this. So I have to redraw. All right. So the atom that's dropping 3 energy levels, that's a big change in energy, which means that's going to result in a shorter wavelength. So let me show this atom where it's, or the electron where it's starting. It's going to drop 3 energy levels. 4, 3, 2, 1. So 1, 2, 3. So it's going to go all the way down here. So this is a big energy change because it's going from level 4 all the way to level 1, which means it's going to have a short wavelength. That means we're going to see a color like violet or like a blue color here. And then the other atom drops 1 energy level. So for example, this could be, let me label these. This could be 3 to 2. It could be 2 to 1, 4 to 1. It doesn't matter. But what's important here is that it's a small energy change, which means this is a long wavelength. And we would see like a red, orange, yellow-ish color. So there's a question, it's similar to this on the performance test where you have to draw a model and explain it. So when you're drawing these models, again, remember they're generic models. They're not specific atoms on the periodic table. So don't try to draw the Bohr model. And also just to review, how we see these colors is that first we have, and let me see if I can just add this here, just so we can go over this. We have an electron that first gets excited. So it jumps up a couple levels. That electron, after it gets excited, it's going to come back down and it's going to fall back to wherever it originally started from. And when it falls, it releases this wavelength. And depending on the energy change or how far the drop is, that's what's going to determine what color you see. So just a refresher on how we see light. So again, the electron first jumps up however many levels depending on how excited it gets. And then after it jumps up those levels, it's going to fall back down. And when it falls back down, it releases a wavelength. And depending on this energy change, that's going to determine the color that we see. Oops. All right. Next one is drawing a Bohr model and Lewis structure for these atoms, identifying the number of valence electrons. So for sodium, if we look at the periodic table, sodium is in group 1. So that means it's going to have 1 valence electrons because that's the trend. Every element in the same group is going to have the same number of valence electrons. It has 11 electrons, so I'm going to put the first 2 in the first shell, and then 8 in the second shell, because that's the max it can hold. So that's 8, 9, 10, and then 11. So the other way you can tell how many valence electrons it is by looking at the outermost shell, which is this shell right here. That's the valence shell. That tells you how many valence electrons you have, which is just 1. So that means our Lewis dot structure is just going to look like this. This is in period 3, and then group 1. So periods are horizontal, groups are vertical. Next one is oxygen. So oxygen is over here. It has 8 electrons. So let me start filling this out. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then the valence shell is this shell right here. And in this shell we have 1, 2, 3, 4, 5, 6 valence electrons. So that means my Lewis structure, 1, 2, 3, 4, 5, 6 is going to look like that. This is in period 2. And then the group number for this one is group. You can write 16 or 6A. Those are both correct. And then neon. Neon is in group 18/8A and in period 2. And it has a total of 10 electrons. Remember, we're using the atomic number to figure out how many electrons it has. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the valence shell tells us, and the group number also tells us how many valence electrons we have. So for this one, we have 8. Or because it's in group 8, we can also tell that it has 8 valence electrons. So the Lewis dot structure looks like this with 8 electrons. All right. So now moving on to the next one. So here we're going to label the periodic table below with the arrow trends for increasing electronegativity, atomic radius, and reactivity. And then we're just going to explain those trends. So for this, let's use a couple different colors. So let me use red for electronegativity. So electronegativity is how tightly / strongly atoms hold onto their electrons. So this trend is increasing to the right side of the periodic table and increasing up a group. So it's how tightly they hold on to electrons, meaning if they're holding on to those electrons pretty tight, they're not going to give them up. Versus if their electronegativity is low, they're going to give up those electrons pretty easily. All right, let's do the next one, which is atomic radii or atomic radius, which is how big atoms are. And this is increasing to the left side of the periodic table, and it's also increasing going down a group. And then the last one is reactivity. And we have 2 for reactivity that I'll write on here, but let's go over what reactivity is, which is how strongly they react with other substances and then we have metals give away electrons, nonmetals gain electrons. So, actually, let me make this a different color. Let's just go with this so we can show these trends too. So, for metals on the periodic table, since metals are on the left side of the periodic table, their reactivity trend for these is their reactivity increases in this direction and increases going down a group. Versus with nonmetals increase going in this direction to the right side and increase going up a group. So there's metal reactivity and nonmetal reactivity. So how strongly they react with other substances. So those are the reactivity, or not the reactivity trends, but all the trends. Next, let's do a little bit of practice. So rank the following elements from largest to smallest atomic radii. So we have F, C, and Na. So fluorine, if we look at the periodic table, is over here. And then we have, so fluorine, let me see. Fluorine is here, and then we have carbon, and then sodium that we're comparing. Okay, so in terms of the size of these atoms, following the trend, as further left we go, the larger the atom. So that means sodium is going to be the highest, or not the highest, but the largest. And then carbon will be the next largest atom, and then fluorine will be the smallest of the three. And that is based off this trend. So as we're increasing, or as we're going to the left side of the periodic table, the atomic size is increasing. So that's the why. It's because we're using that trend. From which element would it be most difficult to remove an electron, chlorine or magnesium? So let's look at this again. Chlorine is over here. Magnesium is over here. So using the electronegativity trend, which is in red, the one that's further to the right and further up is going to be higher in electronegativity. And by comparing it on the periodic table, that looks like it's chlorine. So chlorine would be the most difficult to remove an electron from. Because it is more electronegative. So it's further up and to the right on the periodic table. And then, how are spectral emission lines created for different elements? Why are no two spectral emission lines the same? No two spectral emission lines are the same because no two elements have the same number again, this means number, same number of electrons or same number of protons. So that's what makes all those spectral line emissions different, like a fingerprint, is because no element has the same number of electrons or protons. And then why does sodium have a higher reactivity in water than lithium? And that has to do with the metal reactivity trend. So if you compare sodium and lithium, sodium is here, lithium is here. Since sodium is further down, it is more reactive. So sodium is further down the periodic table. table, so it is more reactive. I think, oh, and then there's one more. Why does fluorine have a higher reactivity than chlorine? So now we're looking at the non-metal reactivity trend. Fluorine and chlorine, and this is the opposite. So as we go up and to the left, it becomes more reactive. So fluorine is more reactive. Then chlorine, because it is further up the group. Because it follows that non-metal trend. So if it's further up the group, it's going to be more reactive. And that's it. Good luck studying for your performance task 6 test. And hopefully you found this helpful.